Welcome everyone to tonight's machine learning workshop. We're going to continue our discussion from last week around exploratory data analysis. And I kind of blabbed a lot last time. We're going to dive right in today, get into the code as quickly as possible. If you're viewing this video in its recorded form, be sure to like the video, share with others. I really want to grow our attendance in the community here around the workshops and around Temzee in general, so do me a solid and feed the algorithm. One thing I want to bring up just as a matter of business before we get started is that I have, as promised in previous weeks, and you may have seen this in a email or social media post, added a place on the Temzee website, temzee.com/machine learning workshop, separated with dashes, machine-learning-workshop. This is a page where you can browse all of the past workshops. Not only do we have, embedded YouTube videos here, but we also have any supporting documents like the notebooks that you see me working in during the live stream, any slides and other things like that. So it can be a great resource for you if you want to look back on any of the things we talked about in the past and get caught up to speed. Oh yes, good evening, Cigar. Glad you could be here. Yeah, let me drop that link in the chat. So that's just an easy place where you can find all the stuff from the past. Now, one slight caveat is that last week's recording, for whatever reason, YouTube didn't archive it correctly, which I'm not 100% sure what happened there. Well, and sometimes these pages will occasionally crash. Just refresh it. That's a bug I'm working through. But what I'm saying is, the only thing I can figure out is that YouTube says that if a stream goes for longer than 12 hours, they won't archive the recording. And so I'm wondering if I maybe left the stream on for a long time. If any of you came by an hour after and it said the stream was still going, maybe that's what happened. Let me know if you encountered that. But the good thing is that today has a lot of overlap with last time, and I'm going to go through a really quick overview of some of the things that were talked about in last stream, just to make sure that information isn't totally lost. All right. But again, I promise we'll go fast. We'll get started here. So in the spirit of that, I want to share with you the starter notebook for today's material. Remember, the starter notebook is the one that will always stay blank. So you can visit this link and then make a new copy and drive, so rather down here, save a copy and drive, and then you'll have a version you can follow along with. You can make your own notes, you can write your own code, etc. But I will be writing all of my code in this live notebook, which I'll share the link here as well. And as we're working, you can refresh the page and you should see my updated code appearing in the notebook. Awesome. Any questions before we get started? Adjust my windows here. All right. So last week we decided we were going to try and do a modeling task with housing data, and we we're going to try and enter in a Kaggle competition and see how we could get our predictions to stack up to others' predictions. But one of the first steps in doing this is really trying to understand this data set. And as we try and understand this data set, we're going to be going over some basic statistics concepts and how they relate to exploratory data analysis and how they relate to the model we're going to end up using, which is variants of the linear regression model. Either next time or the time after, we'll talk about ordinary least squares regression, which is like the vanilla linear regression. But we're going to find that there are other improvements on the traditional OLS, as it's called in its acronym form, that are even better. And we're going to talk about a couple of the reasons for why that is today. We're going to talk about some of the things that might affect OLS, and as we explore this data set, we're going to kind of bait the hook for in the future when we talk about some of those other topics. But what I really want to get into today is continuing and hopefully concluding our discussion of univariate data analysis, right? This data analysis, when we look at individual features, individual columns of our data set in isolation, and try and really wrap our heads around them, understand what they represent, and see if there's anything notable about them. Particularly areas where we might need to do increased data cleaning, or might have outliers, or all those kinds of things. So we're going to have a big focus on data visualizations today, because those really help us in a visual way spot anomalies or topics of interest within a given feature. And so we're going to practice making these kinds of data visualizations today. And I've kind of broken it up into two parts. We're going to first talk about the data visualizations that are really good for continuous variables. And then we're going to talk about the data visualizations that are good for categorical variables. Again, that dichotomy continues. And we've talked about that being a big way that we can kind of categorize our features, our columns of our data set. So we're going to go ahead and load in some libraries. There's already some code here that is a little bit similar to stuff we did last week, but I have a couple of small tweaks that I'm going to throw in. Last week, we downloaded the data set from Kaggle, and we uploaded it here in the left-hand column. We're not going to do that today, because if you upload a data set here in the left-hand column, every time you come back to the same notebook, you have to re-upload the data set. And it's kind of annoying. So I'm going to show you a way you can get around that. If you make a GitHub repository, as you see here, this is a GitHub repository where I just have a whole bunch of data sets that I've used. I'll share the link in the chat. There we go. This is just a bunch of stuff I've used over the years to demonstrate different data science tasks to students and things like that. And you'll notice that here I've uploaded the folder that comes from Kaggle, the Ames housing data, and it's all inside of here. So if you wanted to do this on your own, you can make a GitHub account, make a repository, and then right here in the add a file, you can upload files, or you can, if you say create a new file, you can give a file name here. And if you add slashes, it will put it inside of folders, right? Each of those is nested folders, but I'm not going to actually do that. I'm just showing you that that's how you could make a folder if you wanted to put files inside of a folder. But we're going to discard those changes because I've already got the data set here. Okay. And remember, when we do our exploratory data analysis, we want the training data. So if I click on train.csv, I'll see a preview of the file. But then if I click on the raw button, it's going to show me the raw text version of the file. It's going to look kind of nasty. But under the hood, this is what our comma separated value, our CSV file, looks like. Okay. But now I can grab this URL, and you'll notice I've thrown that here as a string inside of my read CSV. And now that CSV can be read straight from GitHub. I don't have to do any uploading to Google Colab, and it's just automatically here for me. And anytime I open this notebook in the future, I can just run these code cells. There's no other steps required. I don't have to upload any data. It's going to go and grab it straight from GitHub for me, which is a really cool thing. And once you know about this feature of the pandas read CSV function, you can find any CSV on GitHub and very quickly get it into a data frame, start working with it, start making a mess. So that's one slight variation on what we talked about last week. Another variation is within this folder on GitHub, we also have the data dictionary. They call it the data description file. And again, you can hit the raw version and read all of the contents here if you need something to refer to in order to remember what each of the columns in our data set represents. Remember, there's 81 different columns, which is kind of a lot to keep track of. But I've selected this data set kind of on purpose because it's so many columns that we're going to have to do a little bit of extra work and increase our skills in order to be able to wrap our heads around all these different columns and be able to use them wisely. But last week we read from that file directly and we printed out its contents within our notebook. And to me, that got a bit cluttered because it's a really long output. So if you're scrolling through your notebook, it makes it so you have to scroll forever to get down to your later code cells. So instead of doing that today, I've just dropped this link in here in the markdown. And if we ever need to refer back to that file, we can just click on this link and we'll be able to see that, right? So it's in a different tab, but it's always here readily available and accessible to us in much the same way. Okay. Reminder, we have 1,460 rows, 81 columns, and that a lot of these columns had the object data type. We talked about how there's a lot of reasons why a column could have an object data type, but usually, like 95% of the time, it means that that column contains strings, or at least one string, right? It could have mixed data types, so it could have some numbers, but if there's even just one string in there, it will have an object data type. So typically, these object data type columns are categorical variables, but not always. And typically these integer and float columns are continuous variables, but again, not always. It's a pretty close to true dichotomy, but it's not exactly perfect. I'm going to show you a little bit more advanced, a little more sophisticated way to really differentiate between our continuous and categorical variables later on in the notebook. But this is not a bad stand-in for categorical versus continuous if you didn't have anything else to go off of. We talked about that last time. Okay. So again, the MS subclass column is an example of a column that is made up of integer values, but is categorical. These are the only potential values. The left-hand column is the potential values for MS subclass. It is a categorical variable, but it's been encoded as numbers. That's how the creator of the data set chose to do it. So this is just one example of where that numeric versus object dichotomy is not 100% accurate as to, or does not relate exactly to categorical versus continuous. We also talked about how we've got a lot of missing values, and a lot of these are values that are not applicable, right? It doesn't make sense for a home to have a fireplace quality if it doesn't have a fireplace in the first place. And so a lot of these missing values are not missing data. They're not omitted data or deleted data or accidentally not recorded data. It's just data that it didn't make sense to record for a specific property. So that's something we talked about. And we use df.describe to look at our summary statistics. By default, df.describe only will show us the summary statistics of the numeric columns, but it shows us a lot of important stuff like mean, median, standard deviation, min and max, and the quartiles. We'll be revisiting these quartiles later on when we talk about box plots. So the 25th, 50th percentile, which is the same as the median, and 75th percentiles. And also the min and max will show up in box plots. We'll see that later on as well. We can also get descriptive statistics of the non-categorical columns, of the non-continuous columns, that would be the categorical columns, by saying, hey, df.describe, do it for the object columns, right? By default, it does it for the numeric columns. I'm overriding that saying, hey, do it for the object columns. And notice it can't tell me a median, it can't tell me percentiles for these categorical values, but it can tell me how many good values I have, the number of unique values. That's something that's going to be relevant later on as well. The top value, that is the same as the mode. We talk about mean, median, and mode. Well, we can get the mean and the median of continuous variables, but we can only get the mode from categorical variables. And this is the number of times the mode appears in our data set, right? Now, what we're going to talk about, what we're going to see later on is that really this count of unique values is a better way of differentiating between continuous and categorical variables than is the data type of that column, right? I don't care if a column has strings in it. If there's 100,000 different possible values that that column could take on, well, that's still kind of continuous. It's not a finite number of categories, right? And so the number of categories is going to be a better differentiator, or the number of unique values in a column, rather, is going to be a better differentiator between continuous and categorical than data type is. So we'll use this count of unique values a little bit later on to split our data frame into two separate sections based on the number of unique values in a column. Okay. We talked about making a frequency, quote unquote, frequency table, which in Pandas terminology just means doing a value counts, so you can see the quantities of different categories in a column. And we have a for loop here where we could do this for all of the columns if we wanted to. Again, I'm not going to do that today because it's going to clutter up our notebook, but you can uncomment that and do it. And then we finished off by making a histogram, which shows the distribution of a single continuous variable. I can make histograms for non-continuous variables, for categorical variables like MS zoning, but they don't tell you as much. This essentially is just a bar chart, right? The histogram's been smart and went, looks like he's working with a categorical variable here. Instead of having numbers on the x-axis, let's just put the names of the different categories, and then the height of the bar will be quantity. This is essentially just a bar chart. So Pandas has been smart and made a bar chart for the categorical column. But it's not really the distribution along a range of values. It's not, oh, how many values exist between 100,000 and 200,000. It's just quantities of categories. We're really just visualizing our value counts. These numbers on the right are the heights of the bars. So that's the difference in how pandas would treat those two kinds of variables, one continuous, one categorical. Again, that dichotomy is going to come up a lot today. We very briefly, I believe last time, talked about density plots, sometimes called KDE plots, kernel density estimates, or just density plots for short. We built this with Seaborn. You can make these with Matplotlib and pandas as well, but I think the Seaborn ones look slightly better, which is why we're using SNS here. Right? And we saw that the sale price was a skewed distribution. It's skewed to the right, or positively skewed. This long tail goes off to the right, and it's not a symmetric distribution like we would see in the normal distribution, for example. And that can be an indicator to us that maybe the mean is going to get pulled off of the center of the distribution. It's going to get pulled in the direction of the skew, right? So that's what happens with positive skew. The mean gets pulled upwards. The median also gets pulled upwards a little bit as well, but not nearly as badly as the mean, right? So for skewed distributions, it is more appropriate to use the median to refer to the center of the distribution than it is the mean. And you're going to notice that a lot of our statistical tools don't do that. A lot of our statistical tools still use the mean, even if a distribution is skewed. And, spoiler alert, right? Things like linear regression use the mean to do things, and use other statistical measures that use the mean, even if a distribution is skewed, right? So this is one of the small ways that a linear regression model could get thrown off, right? And these values way down here in the long tail, we might call those outliers, right? They're really far away from the typical data points in the distribution, and linear regression is also quite susceptible to the presence of outliers for similar reasons. They pull the mean off center, and they make our line of best fit think that the best spot for the line to be is maybe a little bit off from where it should be. But we'll talk about that again in the future. This is really just me trying to lay the foundation for, in the future, talking about, well, why is our linear regression not quite exactly right? It's not making the best predictions it possibly could. Well, this is one of the sources of those issues, and there will be a couple of others we'll talk about as well. All right. You can quantify the amount of skewness there is in a distribution. Anything greater than positive 0.5, or I guess anything more extreme, further away from 0 than 0.5 and negative 0.5, would indicate skewness in a distribution. And this does the Fisher-Pearson coefficient of skewness. There's like 10 different ways to calculate skewness. This is one of the common ones. And this is a little bit overkill. You typically won't see people calculating skewness in exploratory data analysis, but because we want to come at this from more of a statistics lens, I want to throw some of these statistic topics in there, skewness being one of them, another one being kurtosis. These two are talked about together a lot. Skewness and kurtosis. Kurtosis and skewness. They kind of come together because kurtosis is another way of quantifying kind of the shape of a distribution. And it talks about how fat the tails of a distribution are. You'll hear some people say that kurtosis talks about how pointy the distribution is in the middle, how tall the peak is. It's technically not what it measures, even though, I mean, if the data's not in the tails, where is it? Well, it's in the peak, right? So it's kind of the same thing, but statistics pedants, pedantic statisticians will tell you that that's not exactly what kurtosis is. It's about the fatness of the tails, and is something that we can measure, right? So you have these different distributions. This is an image from Wikipedia. Let me just open it in a new tab so we can make it a little bit bigger, right? These numbers here are the measures of kurtosis, and the higher the value, the skinnier the tails are. Also kind of the taller of the center, but we won't talk about that. The skinnier the tails are, the higher the kurtosis value, and that's something we can also calculate with SciPy, right? So our sale price has a lot of kurtosis, right? If it was had a kurtosis of 0, it would be as it would have as fat of tails as the normal distribution. Because we have a value that's higher than 0, that means this is I'm going to say it, a pointier distribution than the normal distribution. And it really means it's got a skinnier tails than the normal distribution. Okay? So I'm just really bringing up these two terms so that you can get them in your wheelhouse. There's nothing you really need to memorize or have under your fingers code-wise here. Just know that skewness and kurtosis are two things we can talk about when we talk about the distribution of continuous variables in statistics. Okay, so now we're to new stuff. I want to show you how exactly skewness and kurtosis are affecting, well, particularly skewness is affecting the mean and the median of our data set, right? So we're going to do that specifically with the sale price column, but we could do that with, we change this to any of our column headers and we can make a different graph here. And I'm going to remake that KDE plot that we made above. Okay, so this is the same one we made above, but I'm going to calculate the mean and the median. There we go, but I'm not going to print the mean and the median. I am going to put them as vertical lines, red for mean, green for median, and put them on the graph. Okay, and to see that the mean, the red bar, has been pulled to the right. It's been pulled into the direction of the skew, and the green bar, the median, is closer to what we might think of as the center of the distribution. So that's the effect of skewness in action. Okay. Let's see. Now I want to really divide our data set into continuous and categorical. And I mentioned that we can do that by like take a column and look at the number of unique values in that column. Okay. But we want to do this for all columns in our data set. So for a column in df.columns, right? And we want to say, well, if that column has a number of unique values that's less than or equal to some number, then we want to maybe take that column header, because that's what COL here is, a string representing the column header, and put that in a list. So we have a list of continuous column headers and a list of categorical column headers. Those are just going to be strings, but we're going to divide it up in that way. And because we have these lists of column header strings, that'll make it so we can really easily grab just that subset of columns from our big data frame, the full data frame. Okay. So you may say, well, what should the number of unique values here be? And I have to tell you that there's no exact right answer for the number of unique categories that makes a variable a categorical variable, or makes it so that it has a finite number of options. But I can tell you that if you were to come here and look at the data dictionary, you could scroll down through these, you notice that some of these have a lot more options than others, right? You can see how many categories each of the categorical variables has. And if you find the biggest one, that is the neighborhood column, and there are 25 neighborhoods. Okay, so I'm going to say that that is the threshold, 25. If it's less than or equal to 25 unique values in a column, then it is categorical. If it has more than 25, we're going to make it continuous. Okay, and let's see. Yeah, let's then print, so we don't need this number of unique values, the length of the categorical columns, so we know how many are categorical. Actually, I don't need this here. And then, yeah, Google Colab helpfully fills in the rest. So we have 61 categorical columns, 20 continuous columns. How many were object columns? Do you remember? df.select dtypes object. This is a text cell. What am I doing? df.select dtypes object. Okay, so here's all the object columns. Look at the shape. There were 43 object columns, but there are 61 categorical columns, right? So there was quite a lot of numeric columns. They were numeric, but they didn't have enough different values to meet our threshold here, right? So again, just showing that that object versus numeric differentiation is not perfect. And I think this is a better way of splitting up our columns into categorical versus continuous. Okay. And now that we've done that, that's really going to help us do our graphing, do our plotting today. All right, we're going to make a lot of plots. And within pandas, right, we're going to start off with making histograms, but I want to make histograms for all of our continuous variables. And if I just pass in, if I just call this .hist variable, Pandas will do that for me. It'll automatically make a graph with a bunch of subplots. I'll throw in a semicolon there to squelch that funky output. See, this doesn't look great. It's all kind of squished, so I might want to make the graph a little bit bigger. Let's say fig size is 15 by 20 and bins equals 20. I like to have 20 bins. The default's 10. You do what seems good to you. Okay, bada boom. There we go. We can now easily browse through histograms for all 20, right, continuous columns. And we can see that the sale price, which is down here at the end, is not the only column that's got some issues with skewness, right? The greater living area, great room living area, I'm not sure what that is. It's pretty skewed, right? In fact, there is not really a column that is very uniform, or excuse me, that is not very normal in its distribution. Okay, but I have a question for you. What do you think is going on with this ID column? Why does it just look like a blue square? Seems like the most abnormal of all the ones here. Let's look at it. Oh, capital I. I hate that. Huh. Let's look at the first 20 values. Okay. Well, what's going on here? What is the ID column? The ID column is the row index, right? So if I do df.head, see this number on the left-hand side? We call that the row index. This is an integer value that gets assigned to every row in the data set by pandas. Well, if I output this data frame to a CSV, my row index is going to get included as a new column. And that's what this ID column is. The ID column is somebody else's row index that got accidentally left in the data set. It's not really useful to us. We could drop that column and not sweat it at all. It's not something that's going to be correlated with price at all. It's literally just numbers that count upwards. The only way that this might be relevant is if there was something about the order of the properties in the data set, that like properties at the top of the data set were like older properties and newer properties were towards the end or something like that. If there was some kind of time component that related the order of the rows in the data set to our y variable, then we might care about it. But essentially, this is probably a worthless column to us, and it's just an artifact of how the person who made the data set originally set it up. So that's what's going on there. Don't need to sweat it. We're just going to kind of ignore that column. And in fact, we may even choose to drop that column in the future if we want to take the time to do that. Okay. The other thing I want to point out that we might notice from these histograms is some of these graphs have a big giant bar here on the far left. And then they have like a more normal looking distribution off to the side. Okay. Very weird. Okay. Well, this is another example of something that might have been represented with NA values, right? You can't have square footage in your enclosed porch if you don't have an enclosed porch. So a lot of these are just zeros. Okay? These bars on the left-hand sides are a whole bunch of zeros that exist in our data sets. And we might want to remove those zeros before we plot. Okay? And in fact, I want to try and maybe do that with you a little bit later on. We might try and remove some of these zeros and see if it makes some of these funky plots with the giant bars on the left be a little bit more interesting to us. But yeah, that's something to be aware of and something we might spot here by making the graphs, is that there's seem to be a lot of zeros in some of these columns. Maybe there's not as much data in some of these columns as we previously thought. All right? So we can do something similar with density plots. However, Pandas does not have a nice single function that will automatically make all the density plots and put them in a nice grid of subplots for us. We're going to have to do a little bit more of the work on our own. Okay, so we're going to loop over our continuous columns. I guess looping over df continuous is the same thing as looping over continuous, right? It's just going to end up, this variable is just going to end up representing strings of the column headers. But then I can build a density plot for each of these. Okay, and if I do it like so, it's building them one by one, and I will be able to scroll through all these. And you notice the density plots kind of get thrown off by that big column of ones on the left-hand side. Doesn't really make sense to smooth over that, but here they are. Here's what I want to do. First off, I want to do exactly what we did above, and I want to get the mean and the median and throw that on our density plots. So I'm just copied these rows from above. Okay. And the bigger the distance you see between the mean and the median, that is likely an indicator of skewness. Right? So you got a lot of skewness in wood deck square footage and second floor square footage, because we got a lot of zeros, right? Again, those pesky zeros might be coloring our interpretation of this. Oh, the average year since the home was built or remodeled. I guess this is the year since the home was remodeled. It's a strong negative skewness to it. Just wanted to call out the position of the means and the medians, because we kind of talk about them as measures of center as if they're interchangeable, but they're not. They show us two slightly different things about our data set. Okay. Well, you know me, you know I don't like to scroll through my data set. So we're going to throw these in a grid, and we're going to have to be a little bit tricky about this. This line right here builds a grid of axes, a grid of graphs that is 7 rows long and 3 columns wide. So it's going to give us spots for 21 different graphs, which is good because we have 20 different continuous variables. Okay. And now I'm going to need a counter that tells me which graph am I looking at. Am I looking at the first graph, second graph, third graph? So I'm going to make this index variable, I, and I'm going to enumerate this list of continuous values. Okay. And then as I make this plot, I'm going to do something a little bit tricky. By the way, I'm not going to use Seaborn here. I'm going to use Pandas, right? So I select my column. So this is how you would get a KDE plot, a density plot with Pandas /matplotlib. Want to show you both ways of doing it. But then I have to tell it where within my big grid of graphs to put this particular graph that I'm building with this particular column. And there's a really tricky way to do that. And it's like this. You take the index divided by 3, and that will give you the row, and then the index mod 3, and that will give you the column. So sorry, this is integer division. So this rounds by 3, and then it rounds down to the nearest integer. A modulus division divides by 3, but it gives you the remainder after dividing by 3. And this fancy trick will give us, as this for loop runs, the different locations of the different graphs in our plot. Okay? So this is the trick. This is a funky thing. We want to do the same thing, and we want to tell our vertical lines to go on those plots as well, because we want to kind of overlap them. And I think with this, we should get our grid. Oh, something slightly off. Oh, it worked for the first one. And did we get an error message for the others? Let's see what's going on here. We don't want plt.show to be inside of our for loop. We want it to be outside of our for loop. Otherwise, it'll just show at the end of the creation of the first graph. We want the plot to show after the creation of all the graphs. There we go. So same thing we saw above, but in grid fashion, a little easier to scroll through. Again, we've calculated the mean and the median separately. I'm going to take those and I'm just going to throw them directly in the plotting of the line. That way I can reduce this by 2 lines. There we go. Another thing I'm also going to do, you'll notice that some of these words, like density, they're overlapping on other graphs, and it looks a little bit cluttered. Sometimes I can fix that by saying plt.tightLayout, and it will try and avoid any overlapping between the graphs. Very cool. So now we've got this gap between. It's made sure there's no overlapping. It looks a little bit better, a little bit more uniform. And there we go. So this trick, particularly this axis or axes trick, is a really cool way of being able to loop over a bunch of columns in a data set, build graphs column by column, and then stick those graphs into these subplots with 7 rows, 3 columns, 1 by 1 by 1, but then present it as one big plot and make it easier to visualize and see and scroll through and look at our data. So we're going to continue to use this trick as we go, because we might want to do this again for our continuous variables and for other kinds of plots that we make. So we may copy and paste this a little bit and then modify it later on. All right. In fact, we're going to do that, something similar, not exactly the same, for box plots. Sometimes called box and whisker plots. Okay. Box plots, again, help us see the distribution here. And what box plots are really good at is helping us see outliers. Outliers. So let's make a few, and then we'll talk about what the different parts of the box plot represent. You can also see it here in this graphic. Okay. Here's what we're going to do. We're going to loop over our columns. And then we are going to grab that specific column and make a box plot. This time we're going to call plt.show because we're not putting it in subplots. We're not putting it in a grid. We're just going to let these get spat out one after another. And because the box plots are kind of wide, it won't be too big of a deal. Okay. We can see some of them here. Okay, so we're going to make a couple of changes. I don't think this is a good use of space because the plot is rather thin. Okay, so what I want to do is I want to make these plots show up kind of horizontally. So I'm going to say vert equals false. And then I'm going to make the fig size also kind of elongated horizontally. So fig size 5 by 1. So it'll be 5 times wider than it is tall. Okay, now it's a little bit better use of space. Let's look at sale price. Okay, so we see the edges of the blue lines. This top tick mark here, that is the minimum value. This top tick mark that's kind of covered up here by these circles is the maximum value. The box represents the distance between the 25th and 75th percentile. Okay, so that's the 25th percentile, that's the 75th percentile. Make this a little bigger. And then the green bar in the middle, that is the mean. Right? And then any circles we see showing up, those are data points that the box plot has determined to be outliers. Okay. Now you may have heard of outliers before and think outliers are somewhat rare. They're supposed to be data points that are anomalous or really different from the other data points we have in our graph. But you look at some of these, we've got a lot of outliers. Okay. Well, I want to tell you why that is. That's because outliers are determined in a very formulaic way, as explained down here. There's generally two main methods of determining outliers. There's a method called the 1.5 times the IQR. IQR stands for the interquartile range. And the interquartile range is the distance between the 75th percentile and the 25th percentile. So it is the size of the box in the box plot. Right? This max minus min of the box in the box plot, that is the interquartile range. So we take the interquartile range, we multiply it by 1.5, and then we add that value to the 75th percentile, and we subtract that value from the 25th percentile. And if there's any values more extreme than that, then they're considered to be outliers, right? So we take this box, we elongate it by 50%, we put a 150% width box on the right, 150% width box on the left, and if there's any points more extreme than those values, then they show up as circles in the box plot. They show up as outliers. Another method is something called the z-score method, where a z-score is basically the number of standard deviations that a data point falls away from the mean. So if there's a data point that is plus or minus 3 standard deviations, or plus or minus 3 z-scores, then it will be determined to be an outlier. I'm pretty sure these plots are using the 1.5 times IQR method. Okay, but it seems wrong to me that there would be so many outliers in the square footage of basements. It just seems so weird, right? And so many outliers in the size of lots, right? People have talked about, well, if you have outliers, maybe they are what's the word? Distorting your data so much that you should drop those rows. You should drop those observations from your data set. Well, if I were to do that, I don't know if I'd have any data left. It seems like we might be rushing to that conclusion. Okay. So what I want us to do when we think about outliers, ask ourselves some questions, right? Are these valid observations or are these errors? Are these really observations that are so out of whack that they are not representative of the real world, right? Because remember, my number one goal is making a model that generalizes to unseen data. That when I look at new housing data coming in the future, it's going to be able to make good predictions about the sale price of the homes, right? And so if I have some crazy property in there that's really not reflective of the data that I'm going to see in the future, then maybe I want to drop that. But we have to really ask ourselves, is this data representative of what we're going to see in the future? Because if it is representative of what we're going to see in the future, we don't want to drop it, even if a box plot thinks it's an outlier. Okay? So there's some common reasons for outliers, like people have entered the data wrong, like a data entry error, or an instrument that was measuring something malfunctioned or was miscalibrated. Somebody who was kind of modifying or cleaning up the data earlier made some error and the data got messed up. Or maybe the person who's collecting the data didn't collect it in a way that was like a random sample. They didn't collect it in a way that would make it representative of Ames, Iowa, or whatever we assume the larger population to be, right? Those are valid reasons to drop data. If the data is just wrong, if the data is just messed up, well, we don't want it affecting our model. But I think there's something else going on here that we could maybe clean up. Okay. Now, I'll tell you right now that yes, these outliers are going to disproportionately impact our linear regression models. In fact, any models that use distance measures to determine how to fit to the data are going to be thrown off. So that's not only linear regression, that's also logistic regression, k-nearest neighbors, k-means. These are very spatial models that use distances between points to determine how they're going to do their work. Okay? And when we talk about how linear regression exactly is fit in the future, you'll see those exact distance measures. And in fact, you'll see a lot of things akin to distance measures in a lot of our statistical summary statistics. We use squared deviations, as they're called, all the time. And you're going to hear me say squared deviations a million times in the next 2 or 3 weeks, because that is like one of the most core statistical concepts that we're going to run into, right? So any models that use distances, use spatial similarity, that assume a certain distribution, or where the position of the mean is really important to the model doing its job, outliers, skewness, all those things can affect them. Okay? Now, we don't have to use linear regression. There's a lot of other machine learning models that are available to us as well, but we're going to do that because we want to learn about some of the statistics fundamentals that are inherent to these linear models. But tree-based models, like decision trees that we learned about in past weeks, or random forests. A random forest is like, hey, let's not make just one decision tree. What if we made like 100 decision trees? Would that model be better, right? So random forest is just like a whole bunch of decision trees. And then each of those 100 decision trees like gets a vote on what the final prediction should be. Okay? Tree-based models are less sensitive to outliers because they're not looking for the mean. They're just looking for some threshold, some cutoff, some place where they can divide the data set into different groups that will lead to seemingly better predictions, right? So a lot of the things we're facing today might be a moot point if we chose a different type of algorithm altogether. And maybe we'll do that. Once we're done talking about linear models, fitting the best linear model we can, we'll throw this data into like a random forest and see what a off-the-shelf random forest can do with the data. We'll do that in a couple of weeks. Okay. So here's what I think is really happening and what these box plots might alarm us to. And it comes back to our histograms, right? These columns of zeros are making it so the interquartile range is so tiny, the interquartile range might be all zeros in some of these, so that pretty much anything that's non-zero looks like an outlier. Okay? And really, we might want to treat some of these zeros as missing values, as nans, as NA values rather than just zeros. If we come back up to our df.describe, where we saw the summary statistics being outputted, check this out. The min, so let's look at these percentiles. 0 is the 25th, the median, and the 75th percentile for miscellaneous value, pool area, enclosed porch, open porch. That's bad. That doesn't really make sense if these are truly continuous values. So here's what we're going to do. We are going to remove those zeros from our box plots. And we could remove them from our histograms as well. If we have time, we may go back and do that. But I want to show you how we can remove just those zeros from our box plots and see if that makes the box plots look a little more useful, or makes it so that there's not this wackiness with outliers going on. So here's what we're going to do. For whatever column we're looking at, right, I want values that are not equal to 0. Tell me when that column is not equal to 0. And those are the points I want to keep in my data frame. right? So I'm going to make a new data frame where my specific columns values are not 0, and I'm going to call that a temporary data frame, temp or something like that. Okay. And let's see. Yeah, and now instead of building my data frame off of the whole data frame, I'm going to only build it off of the rows where that particular column is not 0. So I'm going to build that off of temp now. And this will omit all of the zeros from our box plots. And it looks a lot better. Looks a lot better, right? Still quite a lot of outliers on some of these. Like, look, there's some really expensive homes. These two homes, probably outliers, right? But that doesn't mean that they're bad data, right? There's definitely expensive homes that exist. They're just not as common as average priced homes, right? But this has cleaned up our box plots quite a lot and has really improved the identification of outliers. And I bet if we were to tell our box plot here to use the z-score method, it might be even better. Let's see here. Pandas.plot.box. I'm going to see if there's like even a way I can by default tell it to switch to use the z-score method. I'm not seeing it right off the bat, but maybe we'll explore that later. Long story short is those zeros are a data cleaning issue. How we treat those zeros is going to be really important to our model because it's going to throw off our model. It's going to throw off the mean and the median and all those sorts of things. And we might want to treat some of those zeros like missing data rather than just zeros. All right. And we may not have caught that. We may not have discovered that. We might not have seen that wonkiness had we not taken the time to make these data visualizations, which is why we do it. It's why we take the time to do all this. All righty. Okay. Not 100% sure what I've got some things in my notes here. I'm not sure what I was trying to show. I think we're just going to delete these two code cells. And we're going to move on to plotting of the categorical features. Okay? This is a little bit more straightforward. Some of these categorical features, the univariate plots are not super interesting unless we have a deep understanding of what that column represents. Let me show you what I mean. Here's the columns we've deemed to be representing categorical data. And MS zoning is one of these. Okay? If I grab MS zoning and look at the value counts, okay, we've seen this in the past, right? We saw that the histogram plotted some of these things. Well, now we're going to use a bar plot, and it's going to make a plot that is very similar to the histogram we saw above. Even though technically it's not a histogram, okay? It's really just a bar chart. If I grab this MS zoning column and I just try and call .plot right off the bat, it's going to say, there's no numeric data here. I can't make a graph without numbers, right? And that's because it's full of string values, right? These string values on the left and the quantities of string values on the right. Okay? So we can't make a chart out of strings. We have to have numbers somehow. So we can use this value counts, though, to make a plot because it has numbers. It has these quantities on the right-hand side. So I can then say .plot there. Okay? But this plot is not what we want. By default, in Pandas, when we call .plot, it gives us a line plot, a line chart. And line plots are more useful when we have data that's changing over time. And we could make some plots like that. Like we have the year built. We could plot like the average home price by year and show it going up and down in a line chart or something like that. That might be an interesting thing to do. But I don't want a line chart here. I want to say, hey, make me a bar chart. And you'll say, Ryan, we've already done this. The histogram above did that same thing. Well, first off, this looks slightly better than the histogram. because the labels are actually in the middle of the bars. I don't know if you noticed that. You probably didn't unless you'd made a bajillion histograms. See how they're misaligned? What the heck? How does that even happen? Well, that's because it's trying to make it, okay. But the bar chart on its own is like not super interesting. It's kind of visually just shows us the numbers we would have seen in the value counts. So let's try and make it a little bit more interesting, shall we? First off, just a couple of tiny details. If you don't like the vertical bar chart, you can make it horizontal with bar H. That may tickle your fancy occasionally, but we can also use these crosstabs. Now I'm only going to make one of these because truly this crosstab is going to be an example of bivariate exploratory data analysis. We're going to look at two columns at once, but I'm showing it to you for a reason, because while I'm showing you the syntax of making the bar charts, it's going to be really interesting to show you the difference here. So, crosstab. Here's our crosstab. Remember, it shows us how the different combinations of categorical variables line up and their different counts. And I don't have very many numbers here because there's not very many houses that have alleys next to them. Okay. But if I say dot plot kind equals bar, now I can see the relative quantities of the different zoning types and how many of them have gravel versus paved alleyways. The reason why I really want to show you this is because now we can make one of my favorite kind of graphs. Oh, I meant to do the crosstab down below. I'm going to slide this down. You can make one of my favorite kind of graphs. It is called a stacked bar chart. And I guess I meant to make that down here. Okay, so let's do this. We're going to leave our crosstab up here and then put the graph down here so we can see both the crosstab and the plot that results from it. Okay, so there's the crosstab, there's the plot, and here's what a stacked bar chart looks like. Same thing, but instead of leaving these quantities side by side, I've stacked them up in a bar. And sometimes that can be extra informative, extra useful for some of these categorical columns. Now, I'm not going to make more stacked bar charts today because we're going to do a lot more of that next time. But I just wanted to show you this particular chart type of stacked bar charts. It is probably one of my top 3 favorite chart types for categorical data. And crosstabs help us compare categorical columns to each other. Okay. Another fancy trick we can do with our categorical data is to use something called a group by. A group by, right? So if I say, hey, group all of my rows of my data set by MS zoning. Well, what does that mean? Well, if I just run this, we're not going to see anything. Pandas is going to say, congratulations, you made a group by object. And it's like, well, thanks, Panda. That's not really helpful. So what I like to do whenever I make a group by is to then cast the results of that group by to a list. Pass it into this list function. Okay. And here's what's going to happen. This doesn't look as nice as I thought it was going to look. That's because we have so many columns here. Well, that's a big output. Okay, so here's what's happened. It has divided up our data set into 5 different data sets. One that is the FV zone, zoning property type, right? And it's essentially divided. Let's see, can I just, okay, I've got this as a list. For group in this list, print group 0. Okay, so here's the 5 groups. There are 5 different categories, and I've essentially made 5 different data frames. Each of those is held inside of this group by object. Okay, so this is the title of the group. and this is the group itself, right? So now I've very easily kind of stratified or broken up this data frame into 5 different groups based on the property zoning. Okay, so casting it to a list here is a nice trick. It's not as nice as I thought it was going to be because we have so many columns, but that's neither here nor there. I'll leave that here. But what we can do is I can say, hey, now that I've got those 5 different groups, let's look at just the sale price column, remember is our Y variable, and let's look at the average sale price by the type of property zoning. So again, this is a little bit bivariate, but you'll have to group by module pandas. Should be a df.group by. Okay. So here's the average sale price for properties in the different kinds of zoning. Notice they differ from one another. And I've got numbers here on the right side, just like I had when I made a crosstab, right? So now I can say dot plot kind equals bar. And now I've got a bar chart of the average sale price by zoning type. So let's add a set title, average sale price by MS zoning. No attribute set title, maybe it's just title. There we go. Average sale price by MS zoning. Kind of cool. We can see that there's differences in our Y variable, that our Y variable is responding or is affected or is related to changes in these categorical variables. And we can get at that by splitting our data frame into groups by the different categories, getting the average sale price per group, and then turning that into a bar plot. This can be one of the most useful kind of plots that we can make with our categorical variables, but again, it's slightly bivariate. I said we're going to do univariate stuff today. This one is slightly bivariate because we were getting the average sale price per category. There'll be more of this next week as we do dive into bivariate analysis. Okay. Last and least, typically people say last but not least, but I'm saying last and least because we can also make pie charts. I don't like pie charts. I won't be shy about that. Pie charts are bar charts, but worse. They're bar charts where it's hard to tell the height of the bar, pretty much. So let's make a default pie chart for MS zoning. Okay, so here's our value counts. Basically, we want slices of the pie to correspond to the number of properties that have that particular kind of zoning. So same thing, I'm going to say dot plot, but instead of saying kind equals bar to get a bar chart, I'm going to say kind equals pie. And there's my pie chart. Isn't it beautiful? Let's throw in a title. And I'll put a plt.show down here so it gets rid of that funky text at the top. So a nice clean graph. There we go. There's MS zoning. And I guess it does help because you can see, oh, visually there's a lot of properties with RL zoning, right? I don't even know what RL zoning is. We come back to our data dictionary here. Residential low density. So that's probably like single family homes. A lot of single family homes in Ames, Iowa. Makes sense to me. Kind of Midwesty. Plains area, etc. Okay. But here's the thing about pie charts. Is this really better than this? I don't know that it is. And there's some instances where pie charts are flat out bad. Okay. So we're going to take a leaf out of our book above where we looped over the columns and made a whole bunch of charts using this axes trick. And the 4 here corresponds to the number of columns. So you just take the number of columns here to help it calculate the row and the column where we want to put it. So let's look at pie charts across all of our categorical columns. Taking a minute to build it. It's crunching a lot of data, drawing a lot of paint, pixels on the screen. Okay. Now let me show you what I don't like. Okay. Pie charts are meant to show parts of a whole. Parts of a whole. And I think they do an okay job at that. We've got some overlap in the labels here. So some of these don't look particularly pretty. I've thrown the legends on so that we can kind of still see what's going on here. But tell me, which is better? Which has more observations, EX or PO in this pie chart? Well, I don't know. How many has more observations here, EX or PO? Which one of those slices of pie is bigger? If you stare at it long enough, you might guess EX is bigger. And you might be right, but you might be wrong, right? Basically, I don't like pie charts because as humans, it's hard for us to compare sizes of pie slices visually. But it is very easy for our brains to compare size of bars. Really easy for us to compare bars and be like, oh, that one's bigger. And you'll also notice that some of these have so many different quadrants that maybe it becomes a little bit silly, right? Pie charts are not always pretty, nice, useful charts, basically. But the world is obsessed with them, right? Like, you will not find a data analytics dashboard without a pie chart. Now, you will occasionally, but almost always they've got pie charts. Or the pie chart's, in my opinion, more attractive cousin, the donut chart. I think donut charts are cool. And I think donut charts are actually maybe slightly easier to tell the different sizes of segments. Okay, and you can do what they've done here. You can label the different sections with particular numbers. That would probably be a really good thing to do. That way you don't have to rely upon your eyes to get it exactly right. But they're just like a fancier bar chart that is not always appropriate to use, whereas bar charts are always appropriate to use. So what I'm basically saying is I'm biased against pie charts. Some pie charts look amazing. Some pie charts look silly and take up space that could be better used for other things. But the world loves them. Every data analytics dashboard out there probably has at least one. So you still got to know about them. They're just underpowered relative to the amount of color and the amount of flare and the amount of flash they put on the screen. And maybe that's why you like them. Maybe they'll impress your boss, right? But or impress like non-data scientists a little bit more than they would impress data scientists. But they're great for categorical variables when we want to show the relative sizes of the different categories, of the parts of a whole. Okay. So they exist. You can make them. Not my favorite. But there you go. Okay. So we've gone fast today. I've been talking pretty quickly. Do you have any questions about the discrepancies between categorical and continuous, outliers, box plots, the importance of visualizing our data's distribution, data issues with having lots of zeros in a column, data issues relative to outliers, a lot of important concepts we've touched on here today. Do you have any questions for me that I could help you answer before we wrap things up for tonight? Thank you for being here. I hope that today's recording processes and the archive is more easily accessible on YouTube. And we are going to get past this really introductory stuff into some really important, really cool stuff next week. It's always a little bit tedious to lay the most basic, most fundamental groundwork. But knowing how to make these plots is important. It's an important part of exploratory data analysis. It's an important part of just data wrangling and being able to have the ability to make subplots and put lots of different columns into a nice graphic where you can scroll through and it doesn't take up your whole screen. Really, it's important to be able to do these things and have these skills and be comfortable with the code that we've written today. So please reach out if any questions come up as you're working through this. To those of you who are watching the recording or anyone who comes across this after the fact, you can reach me on Discord, on Twitter, on LinkedIn, etc. And yeah, thanks for coming, and I will see you next week if I don't see you between now and then. So thanks everyone. Have a good evening.